Hello, fellow problem solvers. So today we're going to be doing some problems from the AMC 10, namely problems 11 through 15. Let us begin with problem 11. So problem 11 really asks us, okay, we have two sequences. One is arithmetic, so let's say the distance is d immediately. So 1d plus 1, 2d plus 1, 3d plus 1. The next sequence is geometric, so let's say 1g, g squared, g cubed. G cubed is the same as. So z we have on both sides. Both sequences are strictly increasing and contain only the integers, and z is as small as possible. So what do we do in a problem like this? Find the value of x plus y plus z. So let's see the most important thing. All of these are integers. So x, y, z is strictly increasing. Strictly increasing means what? It means g is bigger than 1. They're all integers. Oh, look, g is then a positive integer. Now what do we have? Well, now these two need to be the same. This means also that, well, wait, d plus 1 is an integer, so d is also an integer. So now what do we have? We have g is an integer, d is an integer. G cubed is 3d plus 1. And this g and d are as small as they can be. What do we need to satisfy? Well, cube needs to be 1 modulo 3 for this to work. So we can just like try different g's out. G1 doesn't work. And what you get is also like you can quickly realize, okay, wait, x cubed is the same as x modulo 3 by Fermat. And then you might have, okay, so g must be at least 4. So g is 4 is a solution, which will give us what d is. So we'll get here our sequence is 1, 4, 16, 64. We have 1, we have 64. So now we have 3d plus 1 is equal to 64, which means d is equal to 63 divided by 3, which is 21. So we have 21 plus, so we have 22 here, we have 43 here. And now what do we care about? The sum x plus y plus z. So sum these two up, you get 165. You double check it. Yes, it is. It is meant to be d plus 1, 2d plus 1. You sum them up, you get 3d plus 2, 1 greater than this one. Great. You sum these two up. Remember your powers of 2. 64, 128 plus 1, 129. 129. And then what is 4 plus 16? It's 20. 129 plus 20 is 149, which is the correct answer. And that solves problem 11. Let's go onwards. Now let's look at problem 12. So we can think about this in multiple different ways. And this is like the cool thing about like these problems is that there's multiple ways to think about them. But I'm going to just show like the way I consider these problems is, so we have a 4-digit passcode, okay? Exactly one of the digits is even, okay? And exactly one possibly different digit is a prime and no digit is 0. How many 4-digit passcodes satisfy this condition? Okay, so let's think about this. One, and it says possibly different, so not necessarily different, but possibly. Well, there's only one even prime. So let's look at two cases. It has a 2 in it and no 2 in it. If it has a 2, and this is the way I like to think about it. So we have 4 places. Let's say that the even prime is at the first place. So that's where our 2 is. There's only one way to put a number there. There's only one option. And then the other digits, they can't be even anymore. And they can't be other prime numbers. So they can either be 1 or 9. Remember, 3, 5, 7 are all prime. So we have 2 options for this one, 2 and 2. So a total of 8 options. But remember, we have also an option to pick where the even prime is. We have 4 choices for that, which gives us a total of 8 times 4, which is 32 choices of a passcode if it has a 2 in it. Now let's do the other case. There's no 2. Okay, there's going to be an even and a prime. The way I personally like to think about this is, let me first say, okay, in how many ways can I pick where the even one is? Well, I have 4 ways to pick where the even one is. Let's say it's here. After I picked where the even one is, in how many ways can I pick where the prime one is? Well, there's 3 ways. Let's say it's like here. It doesn't matter. And then what's it called? Like those are the 2 most important ones. Okay, so I have 4 times 3 ways to pick the even and the prime. We could have also done this different, like consider like where the prime is and then where the even is. Like the ordering doesn't matter. Now, for the evens, what are my choices? Well, for the evens, my choices are what? Well, I can't pick a 2, I can't pick a 0, and the only numbers I really can pick are 4, 6, and 8. So I have 3 options for this one. For the prime, I have either a 3, 5, or 7. So I have 3 options for the prime. And then again, we're left with a 1 or a 9, 1 or a 9. 2 options here, 2 options here. And that's it. So it's like multiplying all of these numbers through together. And we get that, okay? What do we have? Well, this is 3 times 3 times 3, 27. 27 times 16. And now the way I like to think about this is what? So this is 27 times 16. Do I want that, or do I want to say, okay, this is a 54 times 8? Okay, I mean, I just like to add a 2 every time. 108 times 4. And now 216 times 2. So it's 432. Okay, 432 plus 32. These two together, what do they give me? You combine and you get 464, and we get that's the right answer. So again, the thinking here is how do you best count? There's different styles. My style is this. I like to fix a place first, then say even or prime. That's pretty much it. Let's continue onwards with the next problem. So what does the next problem say? Okay, so we have this infinite figure of squares, and we have this ratio. How do we count we are given what the proportion of the area is shaded? What is K? Okay, so let's figure out how we calculate the shaded area. Now, the first things first, generally, you sometimes want to just take a step back, look at the problem, big picture. What do you see? Well, it doesn't really matter what the side length is. You can scale it up and down, you can zoom in, zoom out. The proportion of the area doesn't change, and the problem doesn't give you that, so you might as well assume something simple for calculations. What is that? It's going to be a 1. Let's assume that the first side length is a 1. Okay, let me draw the square. Now that we have a 1 and a 1, and then it's times k is what is inside. So let's draw that one. Okay, we're going to have a times k. Same center times k. Okay, kk. And now we have this shaded area. Let's shade this area. So we're going to have more shaded areas. But let's think it. So we try to break this infinite problem down into smaller pieces. How can we do that? Well, okay, what do you have? You have an infinite area of these shaded strips. You can think about them in that way. And so what do you do with this? Okay, well, you can just calculate each strip. Okay, let's see. This strip's area is what? Well, it's the larger square minus the smaller one. So what's that? The area of the larger square is 1 squared minus the smaller one is k squared. So that's the area of this strip. Now let us continue onwards. Let us go into 2 more squares. So we have another square. Now the side length is going to be k squared. And then we're going to have a square inside that one with the side lengths being k cubed. Now what's the area going to be here? Well, the area here is going to be, okay, we're going to have k squared times k squared, which is k to the 4th. So we're trying to calculate this strip over here. K to the 4th minus k cubed squared, which is k to the 6th. So every time we have this sort of condition. So you go from 1 squared minus k squared and plus k to the 4th minus k to the 6th plus k to the 8th minus k to the 10th, and so on until infinity. And now the big question is, how do you calculate what this thing is? How do you get 1 squared minus k squared plus k to the 4th minus k to the 8th, plus minus k to the 6th plus k to the 8th minus k to the 10th, and so on and so forth, alternating. There's 2 real ways to think about this. One way, the way I like to think about this is, okay, wait a second, I just take the k to the 4th out, 1 minus k squared. We're always having the side length of one of these squares. You know what that is? We square that, and then we multiply it by this factor, 1 minus k squared. That's going to be the thing that's shared among all. So this is k to the 8th, 1 minus k squared. And we can calculate this using this form. So we can say that this is 1 minus k squared, which has 1 plus k to the 4th plus k to the 8th plus all the way up until infinity. Now, what is this thing in here? It's an infinite geometric sequence, and its value is going to be, so we're going to have 1 minus k squared. What is it going to be? Well, if you have 1 plus x squared plus all the way till infinity, if x is between 0 and 1, actually the absolute value of x needs to be less than 1. What do you have then? Then you have this is 1 over 1 minus x. So here x is k to the fourth. So it's 1 over 1 minus k to the fourth over 1 minus k to the fourth. We can also like simplify this further. But I want to show the other way, which is what does this remind you of? And it's also here good to know like how you get these formulas. And for me, what this reminds me of is if I have some sequence that says 1 plus x to the 2l plus 1. What is this? It's going to be 1 plus x times 1 minus x plus x squared minus x cubed plus x to the fourth minus plus minus plus plus x to the 2l. This is the formula. We learned this formula. And then how do we apply it here? Well, here L is infinite, right? So you can think about it like what happens at infinity? Well, at infinity, if an x is less than, x is less than 1 in its absolute value form. And here what you'll have if L goes to infinity, then this thing, x to the 2l plus 1, this thing becomes 0 effectively. And you get that this whole thing, 1 minus x plus x squared minus x cubed plus x to the fourth minus plus minus plus up until infinity is 1 over 1 plus x. Another way to think about this, and here x is then going to be equal to k squared, and you'll get the same thing that this thing right here is in fact equal to, because this is a difference of squares, 1 squared minus k squared squared, and you get the 1 minus k squared, they cancel out, and you get this is 1 over 1 plus k squared. And now we have, what's the area? 64% or 64 over 100. That's what you calculated. This is that proportion. Okay, again, the reason we put a 1 is because the area is 64% of 1 is just 64 over 100, like the 64%. So now, what do? We can also simplify this, divide both sides by 4, and we get 64 16. This is 25. And then we'll get what? We'll get that 16 plus 16k squared is equal to 25. 16k squared is equal to 25 minus 16, which is 9. K squared is equal to 9 over 16. And then k is equal to 3 over 4. Why is it not negative 3 over 4? I mean, it's not a given option, but also it's because it would be a negative. And we're saying this, we're dealing with side lengths. And they're decreased every single time, and they cannot be negative. And that's it. So the answer is 3 over 4. And now with that, let us continue onwards with the next problem. Like what's fun about this thing, I'll say, is, hey, it's like you're trying to translate geometry into some algebra and just then say, goodbye, c'est la vie. Let's go onwards. So problem number 4. 6 chairs arranged around a circle, on a table, 2 students, 2 teachers, randomly assigned. And then we need to figure out something. We need to figure out like the probability that 2 students will sit in 2 adjacent chairs and 2 teachers will also sit in 2 adjacent chairs. Okay, here's the very cool thing about this. These teachers are, you don't know their names, you don't know the students' names. But really, what you can do here is you can say, well, let's look at them as student 1, student 2, teacher 1, teacher 2. I mean, call them Alice and Bob, John and Jackie, and say that, you say that we're looking at now where we're placing them. And not only that, let's also label the chairs. Now, when we add these extra conditions, making the table sort of distinguishable, that these are different sort of permutations, like we're going to count that, say if we place, that different rotations of the table are different placements. Because what do we care about in probability? In probability, what we care about is the number of total possible arrangements, and we care about the total possible that satisfy the statement, right? So that's what we care about. Now let's look at the total possible number of arrangements. Well, okay. Student 1, they sit first. How many places can they sit at? They can sit at 6. Student 2, well, student 1 has already taken a seat, so they have 5 options. Teacher 1 has 4 options then. Teacher 2 has 3 options, so the total number of possible options is 6 times 5 times 4 times 3. We're not going to calculate what this is because we might be able to do something similar for the total number of possibilities in general that satisfy the statement. Again, let's look at this now. Let's say student 1 sits first. Okay, so student 1 sits, say, here. We have student 1 at the first seat. How many options did they have? They had 6 options for this first seat. Student 2, they sit next. Like, we can choose which order they sit, and the reason we choose the student instead of the teacher to sit next is because again, I think this is a matter of style, like what you think is going to be easier for you to calculate. So for me, it's going to be simpler, like, okay, I just have 2 options for the next student. Now the teacher comes in, and I might see, like, let's say this, like, we place the other student, like, say here, S2. And I see you have a bit of an issue, because if the first teacher sits on the 6th or the 3rd position, so if they sit either here or here, we're going to have just 1 extra option. But if they sit on one of these 2, on chair 4 or chair 5, then we're going to have 2 more options. So what you can do instead is you can just say, like, okay, let me just calculate all the different possibilities of the teachers from the get-go. So if teacher 1 sits here, there's 1 pair for teacher 2. If teacher 1 sits here, there's 2 options. So we're going to have 1 plus 2. If teacher 1 sits here, again, there's 2 options for teacher 2 plus 2. And if they sit in the last spot, teacher 1, there's only 1 option for teacher 2 plus 1. So the total number of ones that work is equal to 6 times 2 times 6. So that's this. Now we need to divide what? We need to divide 6 times 2 times 6 divided by 6 times 5 times 4 times 3. The 6's cancel out. 2 times 6 is 12, 4 times 3 is 12, and we get that the answer is 1/5. And is that a possibility? It in fact is. It's possibility B. For a second there I was afraid, like, oh no, there's no possibility of a 5. And that's the problem. That's a fundamental thing, like when you're dealing with probabilities at this level, is like possible number of choices, possibilities that work. And now let's go on to problem number 15. We have a figure below, a rectangle. What's the area of ABC? Okay, so let's actually do this step by step. What do you draw first? Like, this is my geometry education now going to go really going to show itself. A, B, C, not A, B, C, D, A, E, F, and then we have here a 90 degree. Here's a 90, and here's the D. Okay, we have this a rectangle, so we have this 7, this is 1, this is 7, and AD as a whole is going to be 5. So let's now add some variables. Let's call this x. This is the square root of x squared plus 1. This is 7 minus the square root of x squared plus 1. And then this is going to be 5 minus the square root of... Actually, no, this is not going to be that. The other one is incorrect. This part is going to be 7 minus x instead. It's not everywhere that you have. So this is going to be 7 minus x. And here it's 5 minus the square root of x squared plus 1. Okay. And now you might be thinking, wait, I don't really have anything else to deal with. I'm done with the length and I don't really have a solution yet. Well, there's two sorts of things to look at. When you're done with the lengths that you have on the diagram, there's 2 things you can do. You can add more sort of connect more points together, or you can look for some angles and see if you have something else instead. I'll show both. So one thing we could do is we could say, okay, we don't know what ED is, but we kind of should be able to find it, shouldn't we? Like, is there a way? This is a 1. So, and actually the answer is, well, there is. Like, what we should do to be able to connect them is say connect A and E. And now what do you have? You have the Pythagorean theorem on ABE or AFE, and you have that this length is the square root of 50. Oh, look, what does that give you? Well, that gives you that ED. So you have ED squared plus AD squared, which is 5 squared. So 25 is the square root of 50 squared, which is 50. Oh, wait a second. You have ED is 25. You have this is an isosceles triangle. ED is the square root of 25, which is 5, actually. So this is an isosceles triangle. AED is an isosceles one. Wow! Like, isn't that cool? Yes, it is. You might be thinking, okay, I'm sort of in a time crunch. Do I have something else? Do I have something else? And the thing is like, I mean, you could you do some things? Perhaps. I don't really know. But you sort of need to use now this condition of these two 90 degrees together somehow. And look what you have actually. You have this relationship here, 7 minus x, and you have a 5. So you gotta use that to be able to finish. But that, man, oh man, oh man, I mean, you could do that, but it does look ugly. Does it look ugly? Yes, it does. I mean, let's do it. Let's just do it. So we have 25 plus 25 plus x squared plus 1 minus 10 square roots of x squared plus 1 is equal to, so 7 minus x squared is going to equal 49 plus x squared minus 14x. Okay, so we have 49. Here we are left with a 2. The x squares cancel out. We get 2 plus 14x is 10 square roots of x squared plus 1. What do we care about x? We had the area that we're looking for, ABC, is 1 times x. So that's why we care about it. Like, for me, that's just like very intuitive to begin with. And this means like 1 plus 7x is equal to 5 square roots of x squared plus 1. And now, okay, what do we do? Well, we say we gotta square again. We have then 1 plus 49x squared plus 17x is 25x squared plus 25. Okay, we move everything here, and we'll get what? We'll get 25, so it's 24x squared plus 14x minus 24 is equal to 0. Okay, this needs to have a positive solution. This is a quadratic. We need to solve it. We could plug these numbers in, or, I mean, I see like 24. I mean, first we can divide by 2. We have 12x squared plus 7x minus 12 is equal to 0. Again, not the best sort of thing in the world. Like, we can try to now look at our solutions here and try to guess, like, oh, is it A, is it B, is it C? Like, does any one of them work? How would I factor this if one of them worked? Or you can just like do the quadratic. But frankly, at this point, I thought of dividing by 12 just to make things like simpler, but it's not really simpler. You just the exponent, like the what's it called? The denominator then shows up in your discriminant. But here, if you just do the discriminant, you say you have 49, 7 squared, plus 4 times 12 squared, or 4 times 144. This is your discriminant. And then you're going to have, here you're going to have, so this is going to give you minus 7 plus or minus this, divided by 24. And so now what's here? So again, let's double it. 2 times 288 times 2 is 276. 276 plus 49 is 625. What is 625? Remember your squares. Like, you sort of like get to know your squares very well the more problems you solve. 65 is 25 squared. So you have minus 7 plus or minus 25 divided by 24. And then what do you, that's, so you have like the plus thing. And what does that give you? That gives you 25 minus 7 is 18 over 24. You can divide by 2, and then you get 9 over 12. You can now divide by 3, and you get 3 over 4. So x is equal to 3 over 4, and so your area is 1 times x divided by 2, 3 over 4 over 2, 3 over 8. and that solves your problem. Another way you could get to this same thing and then finish up in a pretty similar way is just say, oh, look, instead of ever connecting these two, you just look at some angles. Namely, you see that, oh, look, if this angle is alpha, so is this one. And so the triangles, I like to write it this way, CAB, so C has alpha, is similar to the triangle because we have a 90 alpha. CAB is the same as CED. And then we can say we have some relationship between the sides. We have that sort of, like, actually we don't really have this same thing, but we'll get something that leads us to the same conclusion, which is we would get that. So x divided by 5 minus the square root of x squared plus 1 is equal to what? What's in the hypotenuse? Square root of x squared plus 1 over 7 minus x. Multiply these through, again, do a similar thing as before, and you'll get the same x as the solution. So that sort of thing works. And there's also a solution that you can just like do trigonometry here as well to like finish this thing up as well. And if you want that, if you want to do that, kind of similar things, similar themes, ideas float around here. What's the best way to figure it out? Again, I think it's a matter of personal style and personal preference, as with like a lot of these sorts of things. And so, yeah, that solves our problems. And as always, I gotta say, thanks for problem solving.